having covered all the basic statistical tests, let's now see some extensions and additional methods that we can use to augment our statistical analysis. Let's begin with confidence intervals, which are actually quite useful, and it's somewhat shameful that we're not going to delve into it more deeply here, but we had to prioritize. Now, confidence intervals is actually a very nice way of combining two different things that we made sure to keep separate throughout our discussion. So there is the notion of significance that we can assess through p-values, saying how significant something is, and then there is the notion of effect size. Given that it is significant and there is some effect, what's the size of the effect? And we've seen some examples where we shouldn't confuse the two. Now, the problem if we just calculate effect size irrespectively of significance is that even if something is significant, we could end up with effect size estimation that could be skewed or biased just due to randomness. And it could actually be quite useful and powerful to combine the two of them together and get some effect size estimate that already accounts for statistical considerations of how many samples you have and stuff like that. So you can think about it as something that actually combines the notion of significance with effect size. Okay, so let's, for example, say that we ran a t-test and we saw that there is some difference in height between, say, Swedes and Japanese, and we want to know exactly what the difference is, and we want it in some way to be robust, to just random perturbations in the data. So something that people very often do is they calculate 95% confidence interval. And if, for example, in this case, we get this confidence interval to be 3 to 5 centimeters, then what it means is there is a 95 probability of the difference being between 3 and 5 centimeters. Okay, and that's actually what it means. It just gives you 95 probability estimate for where the mean difference truly lies. So it means if we run this experiment 100 times, then in 95% we should get it to be the right interval. Now, there are some different ways that people sometimes interpret that, so it could be mistaken in various ways, and that is something we already tried to allude to in the quiz that we gave you 2 lessons ago. So make sure that you're sharp on the exact definition and you don't confuse it, but I won't repeat it here. Other examples can include things like, let's say, we want to calculate, the time scale of the G phase in E. coli, and we can say, okay, it's 15 to 40 minutes. Okay, again, meaning that we're 95% sure, given the evidence that we have, that this is that the true average time is somewhere between these quite wide scale. Or another example, if we go to something, let's say that we use the Fisher's exact test, then we could, even calculate a confidence interval for the odds ratio. And for example, we could say that under consumption of 50 grams per day of alcohol, we see that it has an association with liver cancer with an odds ratio between 1.25 to 1.56. And again, that means given the evidence that we have, we see some association between those two variables with an effect size measured by odds ratio that we are 95% sure is between those values. Okay, and of course, if we want this definition to actually make sense, we also need to explain more carefully what exactly we mean by 50 grams per day of alcohol consumption. Of course, if we accurately measure alcohol consumption, it will never be exactly 50 grams, up to the micrograms. So if you want to actually give it a proper, well-defined definition, I guess you also need to explain exactly what 50 grams per day mean, and also give some interval to which people exactly fall under this category. Okay, so luckily for us, most of the time we can calculate the confidence interval in Python. So if you need to calculate something, just do a quick Google search, and I'm sure you will find it very quickly. Unfortunately, in some cases, we actually don't have off-the-shelf implementation in Python. For example, last time I checked, there wasn't an implementation of odds ratio confidence interval, but luckily for us, it's actually quite easy to calculate. So I gave you here a link of just a simple calculation you can run in Python to do that. But again, in most cases, like if you want for a t-test for a mean difference or for the average and standard things, then you should have a built-in implementation in Python. And again, if you do a quick search in Google, you'll find it. We just don't have the time to go more deeply into this. Okay, next thing I wanted to mention is nonparametric tests. Okay, so we actually saw many different tests, and while going through the test, I mentioned sometimes, please notice that this is a parametric or a non-parametric test. So a non-parametric test, let's clarify the definition, is a test that doesn't make assumptions or concrete assumptions about which family of distributions the data comes from. So for example, you will often have parametric tests like t-test or Pearson correlation that assume normal distribution. And very often you will have a non-parametric version to these tests that doesn't make this assumption, doesn't assume any distribution. So for example, in the case of a Pearson's correlation, you can have a Spearman's correlation, and instead of a t-test, you can have a u-test, which are the non-parametric versions of the same tests. Now, the reason non-parametric tests are useful is they make less assumptions. Therefore, the null hypothesis is less specific. So if you reject the null hypothesis, so if you get a low p-value, that actually justifies a stronger conclusion. So if, for example, you run a Pearson's correlation or t-test, then rejecting the null hypothesis, in theory, doesn't necessarily mean that you have an association. Maybe you just have a validation of, a strong validation of the normality assumption. Whereas if you use a non-parametric test, then you don't need to worry about it, and you can already justify a stronger conclusion. However, it typically comes with some sacrifice to statistical power. And by statistical power, I mean that it's harder to reject a null hypothesis even when it's not true. Even when you should reject it, it's harder to reject it. You need, I guess, more samples to do that. So that's a penalty we pay for using non-parametric tests, and that's, I think, the main reason why people still use parametric tests, because very often statistical power is crucial, and it's not that easy to come up with more samples, and so people are not willing to give up on their statistical power so easily. And also very often there are some empirical results that show that actually, even though it's a parametric test, it's actually quite robust to deviations from normal distributions. And we saw some rules of thumb for different tests. Now again, we spoke about outliers, and non-parametric tests are especially useful when we deal with those kinds of annoying situations, that we have outliers or very small sample sizes or all those conditions in which the parametric tests are starting to show problems. Okay, and that actually relates to the next thing I wanted to show you, which is permutation tests. Okay, so again, we went through quite a lot of different statistical tests, and we saw that for many cases you have an off-the-shelf test that you can just use. But actually, it sometimes happens that we don't actually have an exact statistical test that is ready to use, and we can just use it off the shelf. And in a minute, I'm going to show you an example of that. And then the question arises, how can we calculate a p-value if we want to determine significance? And luckily for us, there is actually a very generic way to do that should, in principle, work every time. So we can just, instead of using a ready-to-use statistical test, we can just come up with our own null hypothesis and write a piece of software that simulates this null hypothesis and tries to randomly generate data many times, seeing empirically how unlikely our observation is given the null hypothesis, which is exactly the p-value. So we can just, through computer simulation, actually calculate the p-value in a very generic way. And it it's very often done by shuffling the pairing between x and y's. Says that's why it's called permutation tests. Okay, now it's a little bit tricky to give a general definition for what a permutation test is. I think the easiest way to understand it is through an example. And once you see enough examples of permutation tests, then I think it becomes very natural to understand how to do that when you encounter the situation that warrants their use. So let's just see an example, a concrete example. Okay, so let's consider this story. Dr. Splinter was experimenting with a highly innovative green mutagen, observing its effect on the Ninja1 gene in turtles. Within Ninja1, which is 1,000 base pairs long, he observed mutations at 15 different sites. Okay, so we have 15 different mutations in 1,000 base per gene. And now to his great astonishment, he observed a 300 base per region of the gene without any mutations. Okay, so out of a 1,000 base per region, we have 300 subregion with no mutations at all. Now, Dr. Splinter wishes to know if such a protected region could have arisen by chance alone. Okay, so in other words, he wants to get some kind of a p-value to determine whether it's, likely to have just happened by chance. Now, if we consider this story carefully, I think, we can quite easily see that there is actually no statistical test that we learned, and actually no statistical test at all that I know of, that does this exact calculation. It's something, more, it seems to be something more unique in this case. And that's actually a good example to consider using a permutation test. So we don't have an off-the-shelf test to use, so why won't we just try to simulate such genes, simulating the locations of mutations at random and see how likely or unlikely it is to get a protected region of this size. Okay, so let's just go to the notebook and try to do that and actually write some piece of code for this permutation test. Okay, so I'll go to the permutation test section in our notebook. Okay, let's see what we have here. So first we define some constants, okay, based on the parameters that we know. So we know that the size of the gene is 1,000 base pairs. We know that we have 15 mutations. And the gap size that we observed was 300 base pairs, okay? So that's the size of the so-called protected region. Now we are going to run simulations. So we are going to run 5,000 different simulations, which would give us some clue of significance here. Okay, so let's see what the code does. Okay, so we have a for loop that runs 5,000 times. So 5,000 times independently, we want to make the simulation. Now, in each iteration of the simulation, we do the following. So you see, we use the random sub package of NumPy because we want it to be random, and we choose the 15 mutations at random out of all the different 1,000 positions. So it could be 0, 1, 2, 3, all the way to 991. So all the possible indices for the mutations. And we choose them without replacement, okay? So we know that there are exactly 50 mutations at 15 different sites. We don't want the same site to appear twice. Now, that's not the most efficient way to do it, I will tell you, but it doesn't matter. We run it only 5,000 times, and it's a convenient way to do that. So this will give us 15 different random sites that distribute uniformly across this 1,000 base pairs region. Okay, so we take those 15 locations, and first we sort them from the lowest to the highest using NumPy sort function. And we use the NumPy diff function to get the differences between each consecutive site. So if, for example, we have location 100 and then 150, then the difference between them is 50. And we know that this is the gap size between them. And at the beginning, we concatenate a 0, and at the end, we concatenate the last index to also account for them. So if we have that the first site is 200, then we also want the difference between 200 to 0, which is also a gap in our case, just a gap at the beginning. Okay, so that will give us all the gaps given those random mutation locations. And then we simply take the maximum between them, and that this is the max gap of this simulation of, just randomly simulating 15 random mutations across this entire gene region. Now, that's the crucial part. That's where the actual calculation of p-value happens. Now, if the max gap is larger than the kind of gap that we observed, so we observed, remind you, 300, then we increase the count by 1. So the count is the number of iterations in which we got a result which is more extreme than our result. And again, remind you that this is exactly the definition of a p-value, okay? So p-value is the probability of having an outcome that is at least as extreme as our outcome given the null hypothesis. And the null hypothesis in this case is that the mutations just distribute uniformly. So what we have here is exactly a Python implementation through simulation of a null hypothesis, and that's the way to empirically derive a p-value. Okay, now we can count how many times we have that condition happening at random, and by then dividing it, with the number of permutations that we run, this will give us an estimate of the percentage of times in which we have more extreme results. And anyway, we also want the entire distribution. So we just append the max gap to the sampled max gap. So this, at the end of the simulation, will be a list with the 5,000 numbers that we get. Okay, so again, the one-tailed p-value is just the count divided by the number of permutations. That's like the estimate for the p-value, like we explained. But that is noticed just the one-tailed p-value, okay? Because we only consider the case where it's on the right-hand side of the distribution, where it's larger than we would expect at random. But in some cases, maybe we would also be surprised if the largest gap was also very small. So maybe we also want the two-tailed p-value, which is simply the one-tailed p-value multiplied by 2. Now, in this case, I will grant you it's not at all clear whether we need to use the one-tailed or two-tailed. So let's just print both. And you can see that the one-tailed p-value is on the order of 7%. Okay, so it looks borderline significant, but if we're strict about the threshold of 0.05, then it's not significant. And the two-tailed, of course, is not significant. And also notice that this involves some randomness. So every time that we run it, we actually get somewhat different numbers. Now, 5,000 simulations is probably enough to give us some robust results. So we see that we always get something between 7 to 8%. And of course, the more we increase it, the more accurate it will be and more close to the actual p-value that we would get if we were to make an exact calculation. But yeah, we'll come back to it. But this is another rather annoying aspect of permutation tests. Okay, so anyway, it seems like according to the standard threshold, whether we use a one-tailed or two-tailed p-value, in this case, we wouldn't reject an hypothesis. So even though 300 seems like a quite large gap, and we can see it is quite a large gap, it's on the 7 highest percentile, it's still not very rare, and this could indeed happen at random. And we observed that just through a permutation test without needing any kind of fancy statistical test, just something we implemented on our own. And again, I think this is a good illustration of the power of actually being able to write a piece of Python code, and then you're not really limited by the kind of analysis you can do. Even if you don't find exact statistical test, you can always write some piece of code that will just simulate whatever it is that you want to test, and you can get some empirical estimation for the p-value. And if we want to observe it, visually, we can also visualize what we get. So we take all those sampled max gaps, and you see we can plot their distribution here. And here we plot in red what we observed, 300. So you can see that what we get is somewhat extreme. Okay, it's on the right-hand side of the distribution. It's not that extreme. So we have a tail. It extends all the way to 500 even. Okay. Okay, so although the bulk of the results are smaller than 300, it's not that rare to get something which is 300 or even more. Okay, so I hope this example illustrated how permutation tests can work and that it's actually a quite powerful tool to use. But it does have some important downsides. First of all, like we saw, it could be computationally expensive. So if you want to get good estimate of low, especially low p-values, then it could be it could take us a lot of time, because, if we want, for example, to estimate a p-value on the order of e to the minus 6, then it means we would need a few millions of iterations to do that. And you see it takes time to run that many simulations. And if we're interested in very low p-values, then it's completely impractical to estimate them. So like we said, let's say that the p-value is on the order of 1 to million, then we can run it a few million times and we should get some cases in which we get a more extreme result, and then we can do some estimate of the p-value. But if the true p-value is, let's say, on the order of e to the minus 40, then even if we run it a billion times, we will still get 0 cases in which we get something more extreme. Okay, so we run it 10 to the minus 9 times and we get 0. And now we don't really know whether the p-value is e to the minus 9 or e to the minus 20 or e to the minus 40. It could be any of them. So all of those p-values would give you 0 results in this case. So the most we can do in this case is just put a higher threshold and say, okay, we think that the p-value is below e to the minus 9, but we won't be able to get more accurate than that. And also, very annoyingly, like we saw, every time that we run a permutation test, the results change. And this can be very, very annoying if you're interested in, especially if you conduct a long-term research. So imagine that every time that you revisit and change something in your analysis, then all of a sudden everything changes. And let's say you send your paper to review, and then the reviewers give you some comments, and you try to fix a few stuff, and you run it again, and oops, you get a completely different results. Now you need to change your entire paper. For no good reason. You didn't actually change anything, just, you just get different random results, and it's very annoying. And you can mitigate it to some extent by using a seed to the random. Okay, so this is something that came up in an earlier bonus question, where this bonus question discussed how random numbers are generated and how it actually works. So we saw that random seeds can be useful exactly for this kind of situation where we want to have something that behaves like a random simulation, but still has some deterministic component to it. Okay, so this can mitigate this problem, not to solve it completely, but I think it can be useful to use if you need to use permutation tests. Okay. Now, as a segue to the next topic, let's actually again start with a short story. So in this case, we have an excited young student that was looking for genes that are affected by an experimental drug. Okay, now looking at RNA-seq results of the entire mouse transcriptome, he found a gene that seemed dramatically overexpressed. Okay, so we saw that particular gene that caught his eyes given the observations. Now, to confirm that, he ran a t-test and found a significance level of 2.442 e to the minus 5. Okay, which we consider to be quite significant. So the student reported the exact exciting finding to his supervisor. Okay, so take a minute to think what might be wrong with this story. Okay, so like I said, this relates to our next topic of multiple hypothesis testing. And the problem is that the student did something that is called post hoc theorizing, okay, which is actually cheating. Okay, so if the student had made his hypothesis prior to the experiment, it would have been fine. Okay, so if before seeing any of the results, he, had thought about this gene and had decided that, this gene was a particular suspect, then no problem. You could just then go and run the analysis and, execute this t-test and derive a p-value and see, okay, it's below 0.5, we reject the hypothesis, it's fine. But the problem here is that the student actually looked at the data and only then decided what to test. Okay, and in this case, that actually has very, very strong implications because it's not the only gene. We know that even if we just look at protein coding genes, we have 20,000 different genes. And in this case, where we run, a t-test for each gene separately, it's like running 20,000 independent experiments. Now recall that a p-value threshold of 0.05, what it actually means is that there is a 5% chance of false positive, okay? So even if the non-hypothesis is true, there is still a 5% chance that we reject it for no good reason, just to randomness. So in our case, where we have 20,000 independent experiments, we should expect something like 1,000 positive results just by chance, just by random perturbation. Sometimes we get something that looks like signal, even though it's just noise. Okay, so actually, in this case, it could be very suspicious to just use the standard threshold if we choose which gene to look at only after looking at the results. Okay, so even a p-value which seems as significant as in the order of e to the minus 5, if you run 20,000 different experiments, then sometimes events that with probability of 10 to the minus 5, they occur, especially if you give it like 20,000 times to happen. You can make the calculation and see that it's not very unlikely for something like that to happen just by chance. And that's actually a very big problem when we need to run multiple testing, okay? And of course, it's also something we don't want to avoid. Very often it is something we need to do. We want to test many different things and see which hypothesis we seem to need to reject and which not. And we need some mechanism to deal with it. And luckily for us, it's something that on the last decades has actually been addressed quite well. And there are today many known correction procedures for correcting for multiple hypothesis testing. Now, the two main approaches that we're going to learn is first the Bonferroni correction, which also was the first to appear historically and is the simplest kind of correction procedure. And then we're also going to learn about the false discovery rate, the FDR procedures, which historically came a little bit later. Okay, now we're going to speak about each of them separately. Now, the basic idea in all of those correction procedures is that we need to somehow account for the fact that we don't run just one test, we run multiple tests. And the way that we do it is we create a more stringent threshold. So instead of the 0.05, for example, we can lower the threshold and only accept p-values that are even lower than that. Or an equivalent way to do it, instead of taking a lower threshold, we adjust the p-values into higher q-values, which are like the p-values only after accounting for multiple hypothesis testing, and then we can remain with the 0.05 kind of threshold. Okay, so let's start with the Bonferroni correction. So the idea here is instead of taking the 0.05 chance to reject each true null hypothesis, we take the same threshold to reject at least one true null hypothesis, okay? So instead of having a 5% chance of rejecting each one of the hypotheses, we have a 5% chance to reject any false positive across the entire set. So only 1 in every 20 sets of experiments should return any false positive. Okay, and I hope you can appreciate how powerful it is. Okay, so now, even though we could have as many as we want, we could have as many tests, we could have 1,000, 20,000, a million tests, still we know that we have only 5% chance of rejecting any false positive. Okay, so if we have a million, we have 5% chance of rejecting any one of the million hypotheses. Okay, so it's a very strong tool. Now the way that we do it is by simply taking a lower threshold. So if we have m experiments, we simply divide the threshold by m. Okay, so if we have one experiment, we remain with 0.05. If we have two experiments, we divide it by 2 and we get 0.025 threshold. If we have 10 experiments, it will be 0.005. And for 20,000 experiments, like in our example, it would be 2.5 e to the minus 6. Now, which again, if you remember the kind of p-value that we got in the example with the student, it was on the order of e to the minus 5. So actually, if we did a Bonferroni correction, we wouldn't reject the null hypothesis in this case. It wouldn't be considered significant according to the Bonferroni correction. Now, okay, so we said we could divide the threshold by m. Now, an equivalent way to do it is to multiply the p-values by m to get q-values. And again, instead of dividing, we multiply q-values, and mathematically, I hope you can see it's completely equivalent. Now, the nice thing about the Bonferroni correction is that it doesn't make any assumption whatsoever. So it doesn't make assumption about what kind of tests we run and whether they are dependent or independent. And it also doesn't make any assumptions about which null hypotheses are true. And we're going to see that in both of those kind of criteria that we have, that's actually something that is more subtle if we run an FDR. So in a false discovery rate, it's actually something that we do need to take into account, and we need to be more careful when using it. But if we use Bonferroni correction, it's a very powerful tool, and we don't actually need to worry about anything. We just account for it, and it's fine. Now, of course, like every very powerful statistical method that justifies very strong conclusions, typically the price that we pay is statistical power. So Bonferroni, again, is often considered too conservative. So even when we do have a null hypothesis that should be rejected, Bonferroni correction will sometimes fail to reject the null hypothesis because it requires very, very stringent and very strong significance. So that's the main reason why Bonferroni correction is not used more. And that's the reason why historically people then decided to develop the alternative of false discovery rates. Now, the idea behind the FDR is even more subtle. Now, the idea here is that instead of controlling for the chance of any false discovery like we do in Bonferroni, instead we control for their expected proportion, okay? So what we mean by proportion is we mean the proportion of the false discoveries among the overall discoveries. And by discoveries, we mean anything that we report, whether it's a false discovery or a true discovery, whether it's really it's something that does show, that is in reality have a true signal within it, or it's just random noise. Okay, so the assumption here is that we only report positive results. Okay, so for example, if we test 20,000 genes and we get 1,000 genes to be significant, then people will tend to report only those 1,000 genes, and in their paper they will say something. Okay, we found 1,000 genes to be significant. And now it's very embarrassing if you try to report something like that, and it actually turns out that most of your discoveries are false positives. Even if you got it right for the other 19,000 genes, and you were right to conclude that they were not significant. If there is actually no signal whatsoever in any of the genes, and you still report 1,000 genes, it's still very embarrassing. And that's why FDR makes the very rational assumption that what's important is the proportion of the false discoveries, not among everything, which then we don't even need any correction procedure, but simply among the discoveries that we report. Okay, so if we report 1,000 genes, then FDR will make sure that the proportion of the false discoveries within them is not more than 5% on average. Okay, so among 1,000 genes, we can report 50 genes which are false discoveries, but that's fine, you know, as long as we have 950 which are actually correct genes, then it's not that embarrassing to do that. Okay, so again, just for a quick recap, because I know it can be somewhat confusing. So in our example where we have 20,000 genes, and let's say that we reported 1,000 of them to be significant, then these 1,000 are regarded as the discoveries. Okay, now whether it was true discovery or a false discovery, whether we should have reported them or shouldn't have reported them, we don't know. We only know that we have 1,000 which we reported. And of course, what we want is to make sure that most of the genes that we report are actually true discoveries, or things that we should have reported. And that's what FDR makes sure of. Okay. Okay, so within this family of methods known as FDR, we have some different options. Now again, historically, the main one was the Benjamini-Hochberg version, which was developed in '95, which is considered to be the classic version of FDR. Now what they do again is quite simple mathematically. So what they do is actually comprised of two steps. So first, we take all the different p-values that we get for all the different hypotheses that we generated. Again, let's stick with our example and say that we have 20,000 genes. So in our case, M would be 20,000, and we would first sort them in ascending order, meaning starting from the most significant p-value, the lowest one, all the way to the least significant or the highest p-value that we put in the end. And now for the kth gene, what we do is simply set its Q value to be M times the p-value of that gene, okay, of that hypothesis. So that's the M times pk is exactly what we actually do in the Bonferroni correction, okay? So what we have on the denominator is just the Bonferroni corrected Q value. So in our case of 20,000, we simply multiply it by 20,000. But now the difference between that and the Bonferroni correction is after panelizing each p-value by the same factor of m, we then reduce some of them back with decreasing amounts based on their index. Okay, so each one we divide by k, where k is the index of the p-value. Okay, so for example, for p1, for the most significant p-value, we have k to be 1, so we actually don't change it. We still take the Bonferroni corrected p-value and set it to be the q value. But with the second p-value, for example, after multiplying it by m, we divide it by 2. So we already get something that is twice as significant as just the Bonferroni corrected p-value. And then the more we go on the list, when we get to the 10th p-value, we divide it by 10. So again, we have a quite substantial, factor over the simple Bonferroni corrected q value. Okay, so that's the basic idea. So you can see we do some corrections. So it guarantees that we always get a number which is higher than the original p-value. But we also see that it's much less strict and conservative compared to Bonferroni correction. Now, an important thing to notice about this correction procedure is that it actually makes an assumption about the kind of tests that we run, and specifically it assumes that they are independent, or if we want to be more precise, it assumes that they are positively correlated, but not negatively correlated. Okay, and I'm not going to explain what it means. It's a very technical kind of definition. an important thing, again, to keep in mind is that people have found out, again, that in practice, in many scenarios, it's actually not that much of an issue. So in most, natural conditions, you will have this requirement of positive correlation. But again, this is something that actually needs to be, if you want to be very, very strict and precise, you might argue that actually in most cases it doesn't warrant that kind of assumption to be made. In practice, I will tell you that people actually do use just Benjamini-Hochberg most of the times. And whether it's justified or not, I will not get into it. I mean, I will leave it for you to decide. But that's not just what people do in practice. So most of the time they will use it, and they won't even check this kind of independence or positive correlation condition. But if you want to be more strict and better than what most people do, you can use a different version known as the Benjamini-Cutielli that was developed in 2001. And this is a slightly more sophisticated version, again, slightly more conservative. Okay, so it's a bit more hard to reject the null hypothesis, but the nice thing is that it doesn't assume anything about the dependence of the tests. Okay, so if you use that version, you don't need to worry about it, and it's just fine. Okay, so these are the different considerations. Again, I'm not going to tell you what you should do in your own research. Most people do use just Benjamini-Hochberg, but sometimes maybe it doesn't, not for justified reasons. But anyway, it's important to keep in mind that FDR can be sometimes very non-intuitive. Okay, so here I wrote down a list of some things that can be non-intuitive about this method. Now, the first thing that I think is very surprising, I was very surprised the first time that I learned about it, is that FDR actually provides you with the same degree of assurance as much as the Bonferroni correction, that there is indeed some effects. What I mean by that is when all null hypotheses are correct, okay, so when we shouldn't reject anything, in both cases we have the assurance that only 1 in every 20 sets of experiments should result in any false discovery. And again, I illustrate this word sets of experiments, which is unlike every 20 hypothesis. Okay, so if we just want every 20 hypotheses to result in any false discovery, then we actually don't need any kind of correction. But once we use a correction, it gives us a much stronger kind of assurance that we have that for every 20 sets of experiments. Okay, so every 20 times we report something, we have the assurance that there is indeed some effects. Okay, so actually what it means is that FDR is actually a stronger tool to determine whether there is any effect. So in that respect, it's of course stronger, but so in this respect, I'm sorry, they give you the same assurance, but of course we still have that the overall number of false discoveries will be higher with FDR. Okay, so that's the price we pay for being less conservative. Okay, so we do get more false discoveries, in the unique hypothesis that we test. So again, with the example of genes, we will get more genes which are falsely reported to be significant. So in the resolution of single hypothesis, we get more false discoveries, but as a resolution of whole sets of experiments, we have the same kind of assurance. Okay, so this is confusing, but I think it's something that is important to keep in mind. Another thing that could be somewhat non-intuitive about FDR is the notion that lower p-values are actually punished more than higher ones. So if you remember, in the Benjamini-Hochberg kind of formulation, you see that we divide each p-value by its index. Okay, so the more significant the p-value is, the lower its index, and then it's penalized more. Okay, so the p-value is penalized all the way to the way it would be penalized by Bonferroni, and the last p-value is actually not penalized at all. So if you get k to be m, you see that you get a q-value which is exactly the p-value. Okay, so the more significant a p-value is, the more it is penalized. And in theory, this could lead to some cases where you even have that you start with some p-values and you have that the p-value that was originally lower, that was originally more significant, now ends up getting a higher q-value, which is less significant. So if you just follow this formulation, this could actually happen to you. And now, fortunately, in most implementations, they actually make sure that it doesn't happen. So if you have a lower p-value ending up with a higher q-value than a higher p-value, then the implementation will actually set the corresponding q-value to be as low as the q-value of the higher p-value. So it actually forces it to be as significant as the higher one. And there is some mathematical formulation and some probabilistic calculation that prove that this is actually an okay thing to do, that you can actually do that. Okay, so this is another thing that could be sometimes non-intuitive about FDR. And lastly, there is this whole notion of q-values, which I think, I guess everybody would agree, are even less interpretable than p-values. And if you remember at in the previous lesson when we spoke about the definition of p-values, and we gave it some time and had a very elaborate discussion about what p-values mean and what they don't mean. So if you remember, we saw that it's actually very tricky to actually interpret p-value correctly. So to specify the exact definition and then to have some intuitive understanding of what it actually means is it's not easy, and it confuses even experienced researchers. Now with q-values, it's even worse, I would say, to have a very clear intuitive understanding of what it means. So with q-values, I would advise you to not even try. I think that just the way to think about q-values is just as a very technical thing, just as some kind of an adjustment of p-values for multiple hypothesis testing, which means, again, p-values, the lower it is, the more significant it is. And just according to a threshold, this is the thing that you use to determine whether you should or shouldn't reject your null hypothesis. But any other kind of intuitive explanation, I think, is a dead end. So I think we should just stick with the technical understanding of those strange objects. Okay, now a final thing I wanted to say about FDR, again, another reason why FDR is somewhat more tricky than Bonferroni is the following caveat, which again, I think many people abuse this kind of this aspect of FDR, and I think it can lead to actually bad results. So what's important to note is that when you do FDR, it's actually important to exclude known effects. Okay, so if we go back to the example of genes, let's say we test 20,000 genes. Let's say, we look for, genes which are related to some disease, and we already know before even running the experiment, again, based, let's say, on literature, we know that 100 genes are already known to be significant. They are associated with the disease that we study. Then what this means is that before we do FDR correction, we need to actually remove those 100 genes from the analysis. And the reason that it's crucial to do that is, again, what we're going to report by the time we finish the analysis, we're going to report everything that is significant, but significant and is not already known. So let's say we run the analysis and we get 105 genes to be significant. We're very happy. And then we do some further analysis and we find that out of those 105, we actually see that 100 are already reported in literature and people already know that they are associated with the disease that we study. So what we do, we of course, we might put those genes in the supplementary, but in the paper itself, we write about the 5 novel genes that we discover, and we send the paper to Nature, and we very happily write in the cover letter to the editor that we found 5 novel genes, which we are the first ones to discover to be associated with the disease that we study. But what could actually end up happening is that those 5 genes are completely spurious, because of the exact definition of FDR. If you remember, FDR assures us that the overall number of false discoveries out of all the discoveries is 5%. So in our case, out of 105 genes, it's very likely that we will have 5 genes which are false. That's the kind of guarantee that FDR makes, and we should expect to have roughly 5% of the genes to be just false discoveries. But in our case, we know that 100 are already known to be true genes. So if we know that 5 of them are false, it's very likely that those 5 genes are the exact 5 genes that we reported. So it's very likely that even though we write in the paper about 5 novel genes, all of them are completely spurious correlations, which we shouldn't have come up with in the first place, and they are just statistical artifacts due to the kind of correction that we made. And the reason that we got it is because we didn't exclude the 100 known effects from the analysis before we did FDR. So if we had first removed those 100 genes and then done FDR, then we would have got a list of genes that we can actually believe in, because now everything that we get, we're actually going to report. So, even if 5% of them are false, as we should expect, it won't be that embarrassing, because, these are not like the entire genes that we report in the paper. Unlike the case where we included the known effects, and now it could very well be that everything that we actually speak about in the paper is completely false. Okay, so again, this is non-intuitive, and I guess it's very easy to fall in those kind of traps. So that's the reason we dedicated some time to try to understand that, and I hope this explanation was clear enough. Okay, now to actually run it in practice, okay, no, I'm sorry. Before that, okay, and another thing I wanted to mention about multiple testing correction is that there can sometimes be a nice alternative to what we call the omnibus tests. So omnibus tests are things like ANOVA and the chi-square test that we saw. So essentially essentially tests that can check a bunch of categories together. So we saw, for example, that we can use ANOVA in the case where we have many groups and we wanted to see if some numeric variable is different between them. And we could use chi-square test to test any kind of contingency table that we have to see if we have some associations between the columns and the rows of the table. And in both cases, when we reject the null hypothesis, we don't actually know where the effect actually lies. So in the case of ANOVA, we won't know which group is the significant one. In the case of chi-square, we won't know which exact rows and columns are the ones that correlate with one another. So they're very powerful tests, and they have very strong statistical power, and it's easier to get significant results. But the downside is that you don't have a fine-tuned understanding of where the effect lies, and unless you use the post hoc tests. But we actually can use multiple testing correction as kind of an alternative to these two tests. So for example, instead of an ANOVA, we can run a one versus others t-test. So we can each time isolate a group and then to test it against the others. But then we, of course, will get many different p-values, one for each one of the groups. And we, of course, need to then account for multiple testing correction using FDR or Bonferroni. And in the case of a chi-square test, we can, again, do all kind of pairwise Fisher's exact test. So we can each time isolate a specific row and column in the table and do a 2x2 contingency table, again, defined by one versus others in both the rows and the columns. And again, we then follow by FDR correction because we end up getting many different p-values. Okay, so now let's speak about implementations. So within Python, we can use the stat models package. and you see here the entire signature of the method, of multiple tests method that we can use within the package. So the way this works, we simply give a list of p-values, and we specify the method that we want to use, and we can also give it a threshold, which is by default 0.05. And we then get in return a tuple with 4 different things. Now the last 2 are not important, so I marked them with underscore. But what's important is the first and second return value that we get. So the first one will be a NumPy array with significance, so just trues and false, Boolean values of whether each p-value is significant or not. And the second one will be the q-values that are the adjustment of those p-values. And you can just give it a list of p-values. It could be anything that is iterable, so it could be a list, a NumPy array, a pandas, anything. And you don't need to worry about sorting the p-values, okay? So this function, if for example, you use FDR, it already knows to sort the p-values and calculate the FDR q-values appropriately, and then give you the q-values in the exact same order of the p-values that you got. So you will get that the first q-value corresponds to the first p-value that you gave it, and so on. Okay, so you don't need to sort the p-values. Of course, you can do it if you want before using it. And the method, you just give it the method name. So actually, it supports several different methods, including things we didn't really discuss. For our purposes, we have the 3 different options that we saw. So you could put Bonferroni if you want the Bonferroni correction, or FDR-BH if you want the Benjamini-Hochberg version of the FDR-BY if you want the Benjamini-Equitieli. And that's it. Okay, so let's see code examples of how it works. Okay, so in the notebook, I go to the multiple testing section. Okay, so if you remember, before we had the example of counting using gene code, how many protein coding and microRNA genes we have per chromosome. And we saw that we could use a chi-square test to see that it's actually significant. So we have different proportions of protein coding and microRNAs genes per different chromosomes, but we couldn't really tell which chromosomes were the ones that showed deviation. So now what we're going to see, we're going to actually test each chromosome separately. Okay, so let's maybe take a few minutes to look at the code and see how exactly we do it. I think it will also be a nice recap of the kind of pandas technique that we have learned in the past. So if you remember, we had the gene types per chromosome, which was just a data frame with 1 row per chromosome and just these 2 columns. So just how many protein coding and microRNAs we have per chromosome. And first thing, we want to sum it to get the total number of genes. So remember that pandas summation will just give you the summary across the different columns. So we had 2 columns, and we can see the sum of these columns is just the grand total of the overall number of genes across the entire genome. And if we take the grand total and specifically take the microRNA and divide it by the sum of the 2 numbers, we can calculate and see that we have 8.6% of the genes being microRNA. Now to test each chromosome independently, we define the test chromogenes function, which gets the chromosome genes. So for each gene, it will be just a series of these 2 values. So it will be a series with the index being protein coding and microRNA, and the values being just the numbers of how many genes we have within this chromosome. So the way we run the test is first we take the other genes to be the total genes minus the chromosome genes, and we use here pandas vectorized operation to calculate for each one of these 2 values separately how many we have. So we take those numbers and we subtract the numbers of the specific chromosome, and this gives us the sum of all the other chromosomes. And we can also calculate the frequency of microRNA within the chromosome and within the other chromosomes. So within the chromosome, we just take the number of microRNA and divide by the total. And we do the same for the others using this series that we defined. And now if we take the microRNA frequency within the chromosome and divide it by the microRNA within all the other chromosomes, then this actually gives us the definition of the risk ratio. If you go back to the presentation where we define risk ratio, you will see that this is exactly the definition of a risk ratio in this case. Okay, and it's actually very nice that in this case we can actually compute a risk ratio and not just the odds ratio. And that's because we don't have just a sample, we actually have everything. So we use gene code, which gives a complete coverage of all the different genes. So we don't have just a sample of some random genes, that could be biased in some way, and then we could only calculate the odds ratio. We actually have the whole number. We have the true distribution of the genes, so we can actually compute the true risk ratio here, which is nice. Now, to calculate a p-value, we define a 2x2 contingency table. So we take those numbers of the chromosome genes and we turn them to one row, and then the second row will be for the other genes. And yeah, and we get a 2x2 contingency table. Okay, so the first row will be for the chromosome, the second row will be for all the other chromosomes, and the first column will be for protein coding genes, and the second column will be for microRNA genes. And within this 2x2 table, we'll have all the different counts of the genes. And now we can simply fit it into a Fisher exact test and to get a p-value. And then we can return all the different summary statistics that we calculated for these chromosomes. So we can see what's the frequency of microRNA within the chromosome, what's the risk ratio that we get, and what's the p-value that we get. Now, to run it across all the different chromosomes, we use the apply function that we saw for data frames. So again, we take this basic data frame that just have these two columns, and we apply the test chromosome genes. Okay, so if you remember, if you use apply with axis 1, then this will actually run row-wise, and for each row, you will get that the function runs with the pandas series corresponding to this row. So in our case, each row is a series with those two values, with the protein coding and microRNAs, like this function is designed to accept. And now for each time that you run this function, it returns a series. And the reason that we indeed converted it into a series is that then pandas knows to automatically return a data frame with each one of those indices of the pandas series as a distinct column. So when we use the apply, what we end up getting by pandas is a data frame with those three columns, again with the same index of each different chromosome. We get those values, and then all we need to do is simply to concatenate the gene types per chromosomes of the first two columns with these three other columns, and we do it again with axis 1 because we want to concatenate it column-wise. And this gives us a data frame with all the 5 columns, and again, corresponding index. And then we can simply take this data frame and sort its values by the p-value. And then we get everything from the most significant chromosome to the least significant chromosome. And as you can see, the chromosome 14 seems to be the most significant with a quite low p-value. But we are here in the business of multiple testing correction, and as you might have guessed, we now need to do multiple testing correction to account for the fact that we tested 26 different chromosomes. Okay, so to do that, we import the multiple tests function from stat models. And like we saw, we can now run it with the gene types per chromosome, just to give it the whole column. It will be all the different p-values that we get. And we can do it twice, one with the method of FDR Benjamini Hochberg, and once with Bonferroni. And as I showed you, this gives 4 values back. So the last 2, we don't care about them. We just put underscores. The first one is the significance, which we then assign as a new column. And the second one is the Q value, which again we assign into a new column. So all the values that we want, we simply assign them back into the original data frame as new columns. And what we end up getting is that now the data frame is extended and has those 4 additional columns. So you can see that now for each one of the chromosomes, we now also have whether it's significance according to FDR and according to Bonferroni, and you can get the corresponding Q values. And like we expect, the Bonferroni is more conservative. So with Bonferroni, we just get 3 significant chromosomes, whereas with FDR, we get 5 different significant chromosomes. Okay, so I think this is a nice example that illustrates how we can use multiple testing correction as a nice alternative to a chi-square omnibus test in this case. Okay, now we can actually determine which kind of chromosomes are actually significant. Okay, let's see another case. This time we can see how we can use it instead of an ANOVA test and just use all kinds of t-tests to determine, in the case of a numeric versus categorical variable. So here we use the variables on genome length per genus that we defined earlier. And from that, we create this nice plot that shows you for each of the 7 different viral groups that we work with in ViralZone. You can see the distribution of genome length within this this group. And also note that this is actually in log scale. And for each group, you can also see how many samples, how many different genera of viruses we actually have representing this group. And I hope you can appreciate that we have pretty stark differences between the different groups. Okay, so for example, for double-stranded DNA viruses, we get something on the order of tens of thousands. And say for single-stranded DNA, we get something much shorter, just slightly above thousands. Okay, so it's order of magnitudes difference. Now we may want to check whether it's significant, and for that we need to use multiple hypothesis testing correction. And by the way, I think I will skip going through this code. Even it does have some interesting, I think it's an interesting illustration of different things that we learned. So you have some illustration of how to use group by and how to use the zip function with this kind of args syntax that we saw when we use a bunch of time the map function in somewhat non-intuitive way. So I do recommend you, by the way, to, if you have the time, to go over this code and try to dissect it and make sure that you understand it. So I think it's actually an interesting piece of code that actually does, in a very compact way, a quite complicated analysis. It's just that right now, I think we don't have the time to dive into it. And like I said, it's mostly a recap of things we've already learned in the past. Okay, so I won't go into this code, but I do recommend you, if you have the time, to check it out. And let's go straight ahead to the code that actually does the testing. Okay, so let's see what we do here. So first we want to calculate the global genome length average across all the different genera. So we have in ViralZone, I think somewhere around, I don't know, a few hundreds of genera, and we take their average genome length, and we see that across the entire viral world, we have an average genome length of 45,000. Okay, and now for each one of the 7 groups, we create this data frame that tells us how many representing genera we have, what's the average genome length, and what's the standard deviation of the genome length. And again, this is a direct follow-up of the code here. I'm not going to go into it, but again, I recommend you to check it out and make sure that you understand exactly how it works. It's a good recap of pandas and other Python skills that we learned. Okay, so now that we have a data frame with those 3 columns, we also calculate the average ratio, which is simply the average of this particular group divided by the global average, okay, of 45,000. So for example, single-stranded DNA, they have on average a genome of size 4,000 nucleotides, which is only 8% of the global average of 45,000. Okay, so we see very different numbers across the different groups. Now, to calculate a p-value for each specific group, we define this function that receives the name of the group and the length of all the representing genera within the group. And what we basically do, we do a one versus others t-test. So we take the lengths of this specific group, and we take the lengths of all the other genera, and we then do a t-test between them using of course, the unequal version. And yeah, in this way we get a p-value, you can see, for each one of the 7 groups separately. And yeah, we apply this function to get the p-values, and then we sort it according to the p-value, and finally we do this kind of Bonferroni correction to get whether each group is significant and what's the Bonferroni Q-value. And you can see that in this case, we have all 7 groups to be very significant, even with the conservative Bonferroni correction. And actually, to be honest, the fact that we got such significant p-values, and I didn't even have to run the test. I could see it straight away from the plot that it's very significant. That's the reason we could afford to use a Bonferroni and not, say, an FDR correction. So even with Bonferroni correction, we don't have a problem. Everything is super significant. And again, it's not surprising given the plot. We can see that we have very, very large differences with orders of magnitude. And again, you could try all kinds of different variations. So here we use a t-test, and you might wonder maybe u-test is more appropriate because, you know, these are quite strange distributions, and maybe it's not exactly a normal distribution. And another thing, you know, it might be also that even though all the groups are significant, it could be that it's only dominated by some extreme groups. So for example, we see that this double-stranded DNA viruses are much, much larger than all the other viruses. And this difference could actually dominate everything that we get. So even though each of those groups is significant, you know, supposedly on its own, we need to remember that when we calculate the p-value for each group, we actually compare it to all the other groups, including the double-stranded DNA. So what this means is that maybe if we removed the double-stranded DNA viruses from the analysis altogether and just considered the 6 other groups, maybe we would get much less significant results, and even we would get that some groups are not significant at all, because maybe just, you know, all of the groups are significant just because of the difference to the double-stranded DNA. But between them, between those 6 groups, maybe there aren't such, you know, significant differences. I don't know. Maybe there are, maybe there aren't. And we could also try to define it in different ways. You know, maybe we do have differences between, let's say, double-stranded and single-stranded, and the double-stranded RNA, but maybe the single-stranded RNA viruses, the 3 groups that we see here, maybe those 3 groups are not that different from one another. And the only way to find it out is just to exclude the 4 other groups from the analysis and just to focus on these 3 groups. And now, within those 3 groups, to do a one versus others kind of test, or just to do an ANOVA test for the 3 of them together. Okay, so the bottom line is that we shouldn't think it we shouldn't think of what we see here as the definitive way, like to run this analysis. There are many different ways in which we could formulate the question, and each formulation would give us different results. So doing one versus others, including all the others, is not the same as, you know, defining more subtle and specific groups. And there are, even with just 7 groups, there are many ways we can define the categories, and each one of those definitions could give us different results. Okay, so I think we'll stop here, and I hope that illustrated how to use multiple testing correction and the power that it has, and the way it can replace ANOVA and chi-square tests. Now, final thing I wanted to say to conclude this discussion is that this notion of multiple testing correction also, actually, it's related to a different topic that I wanted to mention, of the file drawer effect, which is something that is sometimes also known as the publication bias, and is related to the thing that was popularized as the replication crisis, or sometimes called p-hacking. So all of those concepts, which are very related, what it actually deals with is the understanding, like we saw, that the reason that we need to do multiple testing correction is because people actually tend to report, not to report anything, they just tend to report what's significant. And we saw that within the same study, this could lead to severe problems if we have too many different hypotheses that are being tested, if we don't properly correct for it. Now we can take it one level higher and to consider it from an even higher resolution and see that the same kind of effect can happen within different studies. Okay, so what very often happens is that, again, because of the tendency of people to not, just to move on as soon as they get results which are not significant, and when they get results that are significant, they tend to report them. What ends up happening is that people can work on many different kind of studies, and every time that they come across something which is not significant, they just, put it in the file drawer, hence the name, the file drawer effect. And only once in a while, they actually get something significant, and then they report it. But it could very well be that the kinds of things that they do report are nothing more than just random statistical perturbations. Again, if you use a p-value threshold of 0.05, it means that once in every 20 experiments, you will get something significant. So if a researcher, gets some data, let's say he has some data about, different genes in different tissues. So let's say that at first he had this hypothesis that maybe there was some phenomenon related to the immune system, and he ran a test and it wasn't working. He got a non-significant p-value. So then he decided to test something else. Maybe he tested whether it's related to the brain, and again it didn't work, and then he said, maybe it's related to the liver, and then eventually got a p-value that was significant. It could be just pure randomness, just because the researcher tested so many different independent hypotheses, and that's kind of a more subtle way of doing multiple testing without even noticing that you do multiple testing, because you don't consciously think about every time that you generate a new hypothesis as generating multiple hypotheses that you then need to correct for. And people very often don't do it. And even if we have a very, a very self-aware and honest researcher, we still have the same problem in an even higher resolution of different researchers in different labs. So maybe there is something that drew the attention of many different researchers, and all of them wanted to test it. So all of them had the same hypothesis, which just happened to be false. And then you have different 20 different labs testing the same kind of hypothesis. So if the hypothesis is not true, what you expect by random is that 19 of these 20 labs will not get a significant p-value, and indeed they don't get it, and as a result they don't publish anything. But you have just one of the 20 labs that does, by chance alone, getting a significant p-value, and then this particular lab ends up reporting about these new finding that they find. But again, this is just pure luck. This is just due to chance that they got the significant result. It's just because the 19 other labs didn't report what they got. Okay, so the moral of the story, I think, is that you need to be aware of these kinds of subtle effects, and when you see significant results, just don't think that you automatically need to accept the finding. You should be aware of those kind of things that can happen behind the scenes, and ask yourself some tough questions, including like, how likely do you think it is that the kind of research that you see was influenced by this publication bias? Could it be that what they report in this paper to be significant is just one of many different hypotheses that they could have done just the same, and maybe the result that they published was somehow cherry-picked, whether consciously or unconsciously, or could it be, that many different labs tried to produce these results, and what you see just some random lab that was lucky enough to get more significant results, but it's actually nothing more than that. Okay, so the kind of dichotomous way that people often think about it has, either you have significant versus non-significant. I think this can be a very misleading way to look at things, and you need to adopt, I think, a more kind of a more fine-grained way of looking at it, as like different shades of significance. And it's actually very, very legitimate to actually look at the actual p-values that you get and ask yourself whether those p-values could be just subjected to those kinds of random effects. And it's completely legitimate to treat a p-value that seems to be, like borderline, like 0.04, which is strictly below the significance threshold, but not very much. It's very legitimate to look at it not the same way as you would look at something which is very significant, like, 10 to the minus 7, which is much harder to abuse and do p-hacking on. Even though, again, with modern databases and modern computational techniques, you can even do p-hacking on those levels. So I'm not saying that e to the minus 7 is completely immune to those kinds of effects, and of course there are also other things that could go wrong. So it could be some more systematic bias, or just pure mistake by the researcher. So there are many things that could go wrong, and of course just having a significant p-value doesn't protect you against everything, but at least as far as these random effects and the file drawer effects, I think it actually does matter to consider the actual significance of tests, and to give more credence to hypotheses that are supported by more significant p-values and stronger evidence. Okay, so be aware of these effects, both as a researcher, try to be conscious and not to participate in p-hacking, and also as a consumer of research. When you read about some study, try to be skeptic and have some critical thinking about it. And yeah, and I think by now we have covered so many different ways in which statistical analysis could go wrong. So I hope we understand the importance of being very, very, very careful when doing statistical analysis. But again, this is not to discourage you to do that. Statistical analysis is great, just be careful when you do it. And I think we'll stop here. And on the next part, we will speak about, we'll try to wrap everything up and summarize and conclude this huge topic that has accompanied us for the past 2 lessons of statistical analysis. So stay tuned.